This is a lesson on Precalculus 9.3, a probability section. By the time we're done with this, hopefully you'll be able to identify a sample space and calculate probabilities and conditional probabilities in sample spaces with equally likely or unequally likely outcomes. So to start off, the probability of an event with equally likely outcomes is if E is the event in a finite non-empty sample space, which just means there's something in the sample space, and it doesn't have an infinite number of items or things happening in it, and we call that sample space S, of equally likely outcomes, so everything has the same chance of happening, then the probability of the event E is found in this way. You take the number of outcomes in E over the number of outcomes in S. So the number of outcomes that you're looking for to see if it'll happen divided by the number of outcomes that could happen occur in the entire space, or could occur in the entire space. So an example of this would be if you look at throwing two dice, and you look at their sum, and what I have here is a chart showing the different outcomes. How can you roll a 2? Well, if both dice are 1s, then you'll roll a 2. That happens once. There's 36 different outcomes you could have in rolling 2 dice. Now, you could have outcome of 3. 2 out of the 36 different outcomes will get you a 3. What 2? Well, one dice could be a 1, the other could be a 2, or vice versa, and so on and so forth. So here are all the outcomes possible, and then here are the different probabilities for each one. Once you do that work, figuring that out, you then can find probabilities quite easily. A lot of times when you're looking to find probabilities, there's a little grunt work, if you will, that you have to do beforehand, and then use all the data or all the probabilities that you found to find the bigger picture items. So I won't go through a way of finding all these right now. You could list out all the different outcomes and add them up. You could list out, just to get you started, if a dice was, you could do a tree. I could roll on the first dice a 1, 2, a 3, a 4, 5, or a 6. And then on the second dice, I could get a 2, 3, 4, 5, or 6. And then what you would do is, you'd say what the sum is, what the sum is, what the sum is. And every one of these answers you would get would have a 1 in 36 chance of being what you want. So kind of real quick, that's how you could get all those possibilities. So now we're going to use that information to answer some problems. So if I'm trying to find the probability of rolling a sum divisible by 4 on a single roll of 2 fair dice. So probability of rolling a sum divisible by 4, well, if we look at our list here, what can we, excuse me, what results are divisible by 4? It's as simple as that. Well, 4 is divisible by 4, 8 is divisible by 4, and 12 is divisible by 4. So what we'll do, we'll use that information to help us. The event E consists of these following outcomes, and we use these brackets, these types of brackets, to list what's in an event. So 4, 8, and 12 make up event E. To get the probability of E, we add up the probabilities of the outcomes in E. So the probability of rolling a 4 is 3 out of 36. The probability of rolling an 8 is 5 out of 36. And the probability of rolling a 12 is 1 out of 36. So you can see why I didn't reduce all the fractions up here. It just makes it easier to combine them at this time. Add those three up, and you get 1/4 as your probability. Just to give you another example, you could consider, say you're tossing a fair coin, and you want to know what's the probability of tossing 2 heads in a row on two coin tosses. Well, in that case, you got to think about what's in your set. I could toss 2 tails. I could toss a tail and then a head. I could toss a head and then a tail, or I could toss 2 heads. That's H for heads. That's what's in my set. So there are 4 equally likely outcomes, only one of which would give us 2 heads. So we would have a 1 in 4 chance of tossing 2 heads if I tossed a coin twice and was wondering what my probability of getting 2 heads was. A probability function is a function p, that's what we call it, that assigns a real number to each outcome in a sample space S, subject to the following conditions. The probability has to be between 0 and 1, or equal to 0 or 1. The sum of the probabilities of all the outcomes has to add up to 1. And the probability of the empty set occurring is 0. You don't really need to worry about that. It's just kind of, you got to make sure that there's, you just are clarifying that one of the things is going to happen. You're not going to have nothing happen, because that would throw off your probabilities. So then, I'd just like to talk about the probability of an event with outcomes not equally likely. Let S be a finite, non-empty sample space in which every outcome has a probability assigned to it by a probability function P. So that's just saying that you have some way of assigning a probability to each item that, or each thing that could occur, each event that could occur. If E is any event in S, the probability of the event E is the sum of the probabilities of all the outcomes contained in E. So all that's saying is, if outcomes are not equally likely, whatever outcome we're looking to happen, or looking for to happen, or wondering what the probability of it happening is, we take the probability, we get the probability of that event by taking the way to think of it, it would be to, if event E contains more than one thing, you take the probabilities of all the different things that make up the event E, and that is the probability of event E happening. We'll do an example like that in a little bit. Just want to throw out here the strategies for determining probabilities. First, determine the sample space of all possible outcomes. When possible, choose outcomes that are equally likely. So what that is saying is, make sure you have accounted for everything that could happen. And then, if the sample space has equally likely outcomes, the probability of an event E is determined by counting the total number of outcomes in E divided by the number of outcomes in S. This P parenthesis E parenthesis, that just means the probability of event E occurring. That P means probability. And then, if the sample space does not have equally likely outcomes, determine the probability function, which it means determine how you're going to figure out the probability of each event occurring. Check to be sure that the conditions of the probability function are satisfied that we read through earlier. then the probability of event E is determined by adding up all the probabilities of all the outcomes contained in E. Same thing we mentioned before. So here we'll go through a couple examples. Dylan opens a box of a dozen chocolate creams and offers 3 of them to Russell. Russell likes the vanilla ones the best, but all the chocolates look alike on the outside. If 5 of the 12 creams are vanilla, what is the probability that all of Russell's picks are vanilla? So if 5 of the 12 creams are vanilla, what is the probability that all of the ones that he picks are vanilla? Remember, he's taking 3 of them. So to determine this, first we have to determine how many ways he could pick 3 chocolates out of the box. Well, you know how to do that from section 1. If there are 12 different chocolates to choose from, he can pick any 3 of them, and it wouldn't matter what order he picked them in. So it'd be a combination problem. 12 choose 3. So there's 220 total outcomes possible. The event E consists of all possible combinations of 3. That's what we just talked about. So then what we want to look at is how many different ways could he have picked all 3 to be vanilla? Well, there's 5 vanilla, so he could have picked, if you take 5, choose 3, that's the total number of ways he could have picked all 3 to be vanilla. That equals 10. So his probability of getting all 3 creams vanilla, or all 3 chocolates vanilla, would be 10 out of 220. The total number that he wants, or the total number of ways of getting what he wanted, divided by the total number of ways possible of picking the chocolates, which is 1 over 22. So that's the probability. We'll revisit this question and actually solve it another way very shortly. There's what's called the multiplication principle of probability. Suppose an event A has probability P sub 1 and event B has probability P sub 2. Under the assumption that event A occurs, then the probability that both A and B occur is going to be the product of those 2 probabilities. So now if we look at that same exact chocolate problem again, what we can do is we can talk about what's the probability that Russell picks the first chocolate to be vanilla. Well, that's going to be 5/12. If that happened, what would the probability that he picked that the second chocolate would also be vanilla? Well, that would be 4/11. Because now there's only 11 chocolates left, and 4 of them would have had to have been vanilla. And then the probability that the third one, assuming that both of those events occurred, the probability the third one would also be vanilla would be 3/10. You multiply those 3 together, those 3 probabilities together, and you get the same exact answer. So there's another way to solve the same exact problem and get the same exact answer. All right, so the next note here, a conditional probability formula. If event B depends on the event A, then the way this first part is read here is the probability of B given A is going to equal the probability of A and B occurring divided by the probability of A occurring. Let's write that down. I'll go through an example later. Maybe I'll just keep going through some more notes that you got to write down, and then we'll go through a bunch of examples here. Here's binomial distribution, how that is applied. You can suppose an experiment consists of n independent repetitions of an experiment. So there's n number of repetitions with 2 outcomes called either success or failure. We let the probability of success equal P and the probability of failure equal Q. So then make note that Q would equal 1 minus P. Then the terms in the binomial expansion of P plus Q to the nth give the respective probabilities of exactly n minus 1 all the way down to 2, 1, 0 successes. So if you had all successes, you can get the probabilities of however many successes you want out of the number of attempts you have. And then I've got a little chart here to help you visualize that or look at that. If there's the n number of successes, it would be p to the nth as your probability. Or that would be the term. If there's n minus 1 successes, you'd have to do n choose n minus 1 times p to the n minus 1 times q. So when you have, remember now, p is your probability of success and q is your probability of failure. So that's what this p is, that's what this q is. So this is generally going to be some decimal, and then you raise it to whatever power we're talking here for n minus 1, how many successes you want to see the probability of, times q raised to the number of failures then that you would expect. Because remember, the number of successes and the number of failures would have to add up to the number of attempts, or the total number of repetitions, and so on. So apply this to a problem. If you wanted, say, kind of take this out of your face here, it's jumping at you. If you wanted to, suppose Tommy makes 92% of his free throws. If he shoots 15 free throws, and if his chance of making each one is independent of the other shots, what is the probability that he makes all 15? So first of all, 92% of his free throws he makes. So the P, his success probability, would be 0.92, which means his Q, or his failure probability, is 0.08. If I want to know what his probability that he makes all 15 is, well, that's what I covered up here. 15 successes would be 0.92 raised to the 15th times 0.08 raised to the 0, which is 1. So that probability is not very good. Change it up a little. Suppose Tommy makes 92% of his free throws. Same scenario, only we want to know what is the probability that he makes exactly 10. Well, to get that answer, we would need to do, he took 15 shots, so 15 choose 10 times that 0.92 raised to the 10th times the 0.08 raised to the 5th. That's the probability that he makes exactly 10. So, something to keep in mind, if you went through and found the probability that he makes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15, all those probabilities added together would equal 1. And then remember, where do those numbers come from? From up above, we wanted, we had 15, so your N was 15 in this case, and then the R was 10. This was your P, and this was your Q. And again, this was your R, and this was your N minus R. Well, your notes could end right there, but I just want to throw in a few more examples, and then I'm going to talk about some terminology so you can, if you need some more, or you want some more notes, I'd really focus in on this, or maybe you didn't need those notes and you wanted to skip to this part to start. Well, 19 minutes, that's where you want to start then. I do also want to go over with you how to set up your Venn diagrams, since I haven't mentioned that at all. So to start, for a Venn diagram, we would take and we would have two circles overlapping. The best spot for that. Two circles overlapping. Something like this. And then what you have to decide is, what do you want the circles to represent? And in this case, in this problem, I'll tell you, 54% of girls 54% of students at a school are girls. 62% of students at that school play sports, and half of the girls play sports. So using that information, we can set up a Venn diagram. So it's a Venn diagram. And it was named after an English logician and clergyman, John Venn, and it's really really useful in a lot of ways. It's a really nice visual to use. In this case, would want a circle to represent girls and the other circle to represent sports, because that's what we know the most about right now. And what we know is that 54% of the students are girls. So girls, that total circle is 54% of the student body. So what we know is half of the girls play sports. So if there's 54% and half of them play sports, well, then we want half the girls to be in that circle and half of them to be out of that mixed circle, which would be, take 54% or 0.54, divide it in half, and you get 0.27 over here and 0.27 over here. Well, we know that 62% of the students play sports. So if 62% of the students play sports, then, well, if I have 0.27 are girls, that would leave 0.35 for boys. So now from this information that we have so far, we can talk about, if you look at these percents, it doesn't add up to 1, so the percents don't add up to 100. If you add all those up, that equals 89 or 0.89, which means 0.11 would have to be the space outside of the circles, and that would represent the boys that don't play sports, because in here we've got boys that play sports. Here we got all the girls, and we got girls that play sports and girls that don't play sports. So this would have to be boys, and then the boys that don't play sports out here. So if we wanted to find something out like what percentage of students who play sports are boys, well, then we'd have to take the percentage of boys that play sports, so that 0.35, and divide it by all the boys, or all the people that play sports, or the percentage of the people that play sports, which is 62% of students. And if you divide that out, that would equal about 56.45%, which means 56.45% of students who play sports are boys. If we wanted to know if a student was chosen at random, what is the probability that it is a boy who does not play sports? Well, that's what this 11% is, or this 0.11 represents. So the probability that if you chose a student at random and it was a boy that doesn't play sports would be 11%. This next example that I want to go through is going to describe a situation where you've got unequally likely outcomes. Everything's not equally likely. And what I'll do for this is I'll set up a nice tree diagram that has probabilities on it to help show how you can figure out the probabilities. Here's the situation. You've got 2 cookie jars. One cookie jar has 2 chocolate chip cookies and 2 peanut butter cookies. The other cookie jar has 1 chocolate chip cookie in it. Well, here's the situation. If you look at it as a tree diagram, we've got jar A that we could choose, or we could choose jar B. And then within jar A, if we were just going to reach in and choose a cookie, we could get a chocolate chip, a chocolate chip, a chocolate chip, or I'm sorry, peanut butter, or a peanut butter. But if we chose jar B, we would have to get a chocolate chip. That's the only option. So then what we can do is look at it as you got to choose a jar first. So you've got 0.5 chance of picking this jar A and a 0.5 chance of picking jar B. Now from there, after you've picked which jar, if you picked jar A, you'd have a 0.25 chance of getting any one of the cookies that's in that jar. But if you pick jar B, well then you've got a 100% chance that you're going to get a chocolate chip cookie. Now what you do is you take and you multiply out on each line to get the probability of getting each cookie. So what you do is you take 0.5 times 0.25 to get the probability here. And you do the same thing here, all the way down. This is one of those examples where you do all the work ahead of time and then you can find a bunch of probabilities after. And then the trick is, when you add all these up, they have to add up to 1, which they do. You can verify that yourselves. But now, here's the question. After you do all that work, you can answer a bunch of questions. I'll just answer one here. What is the probability that if you select one cookie at random, that it's a chocolate chip cookie? Well, in order to answer that, at first, without all this work, you might think, well, if I look back up here, I've got 1, 2, 3 chocolate chip cookies out of 5. I got a 3/5 chance. Well, that's not the case. I've got a 0.2125 chance, and here I've got a 0.125 chance, and here this one's chocolate chip. I've got a 0.5 chance. So in all actuality, I actually have a 0.75 or 75% chance of selecting a chocolate chip cookie. Now we could go farther with this scenario, and I could talk a little bit about the conditional probability formula that we talked about earlier. I'll show you what that is again. This one right here. The conditional probability formula. What we could say is, well, suppose we've drawn a cookie at random from one of the jars. And if I told you, you're given that it is a chocolate chip cookie, what is the probability that it came from jar A? Well then, what's being described is we want to know what, given that it, so the probability of it being from jar A, given that it's a chocolate chip cookie. That's what we're trying to figure out. Well, to answer that, we need to take the probability of jar A and it being a chocolate chip cookie divided by the probability that it's a chocolate chip cookie. Well, we did all the work already. So what's the probability of it being jar A and chocolate chip? If we look at our tree diagram here, jar A is here. These top two are chocolate chip. So it's going to be 0.125 plus 0.125, which is 0.25. So it's going to be 0.25 over, and then the last problem we did was what's the probability of getting a chocolate chip cookie, which was 0.75. which quite quickly you'd realize that you have a 1/3 chance. You've got a 1/3 chance that that cookie came from jar A. That's how you do that type of problem. I know this video is getting a little long, but I just want to mention a few more terms. So mutually exclusive means it can't happen at the same time. Like tossing a coin, you can't get heads and tails at the same times. Or if you draw a card, you can't get an ace and a king at the same time if you just draw one card. When two events, let's call them A and B, are mutually exclusive, it is impossible for them to happen together. So the probability of A and B happening together is 0. This is another way of saying A and B, that upside down U. Make sure you make note of that. But the probability of A or B is the sum of the individual probabilities. And when you use that OR symbol, that's the regular looking U. So make note of that. If they're not mutually exclusive, like kings and hearts, turning right and signaling right, those are examples of not mutually exclusive. They happen at the same time. So that's where we could use the probability of A or B happening. This is an example of that. They could happen at the same time. Like hearts and kings. You can see how they overlap in that nice Venn diagram. Then independent events, events not affected by other events, like tossing a coin. It's not affected by anything else. Dependent events, events that can be affected by previous events. Like if you're pulling socks from a drawer or chocolates from a box. Once you pull some out, them being gone affects what you might get after that. All right, I'll stop there. 32 minutes. Enjoy.